All right, so now let's start section 3.10, the related rates. So what is related rates? Well, um, it's you see, guys. It's actually it's a changing of two quantities, okay, and they are related. Okay, that's called a related rate. And for example, if let's see uh, uh, you're trying to uh, put the air into a spherical balloon and do you see that as the radius of that balloon is becoming larger and then simultaneously the volume of the air balloon is changing, right? So you see that the radius of that balloon is becoming larger. Meanwhile, the volume is also becoming larger, and they're both changing and they are related. So this is what we call a related rates problem. And it's a very comprehensive topic for the related rates. For one, it asks you to read the problem very carefully and trying to um, abstract the information point and then rewrite them into like in terms of the equation format, and then using the derivative techniques we learn in this chapter to solve all that. Okay, so there is no shortcut um, to the related rates problem, and most of them are application problems. And what you need to do is really just to practice a couple of problems, and then you can get what's going on. Okay, so in this lesson, I'm going to show you one example, and then after that, I hope you can read through the examples in the textbook and then work on a couple of examples. Okay, so you can get the feelings of like the related rates problem. Okay, so let's get started with this example here. It says like this. Water runs into a conical tank and a rate of 9 feet cube per minute. And the tank stands points down. Okay, since it's a conical tank, and it also gives us that the height of this tank is 10 feet, and the radius of the base, which is 5 feet. Okay. Then it asks us how fast is the water level uh, rising when the water is 6 feet deep. Okay, 6 feet deep. So before we move on, let's see. Um, let's first of all, guys, you have water pouring a conical tank. Okay, so that gives us the shape of that tank. It's also at the rate of this. Okay, that's, and also you can think about it, guys. Is this stands for like the rate of the change of the volume of that water, right? With respect to time. And also the text stands points down. And also give us that the height is 10 feet, radius which is 5. Okay, radius is 5. And how fast is water level rising when the water is 6 feet deep? So basically, what is seeing that okay, I'm starting to pour the water in this tank, and the rate of change for the water of volume is this, and then you will see the water will goes is becoming larger and larger, and then at the moment when the water is 6 feet deep from the ground, and then how fast the water is rising. Okay, so that's the problem. The best way to start for this problem actually is to draw a picture, okay, and then label all the given information, and then trying to link what you already know, and then form an equation. Okay, so drawing a picture not only works very good for our relative rates problem, but also in section chapter 4, it's called the optimization problem, and it's also an application problem. At that section, you will see that drawing a picture, if you can draw that, and it will be very, very beneficial for solving the problem. Okay, so that's the problem. And then now let's try to see how do we realize that. Here we go. Again, my drawing skill is very terrible. Okay, so but as long as you can get a brief idea, we're good. So first of all, this is the conical tank, and then starting to pour water from here. As you can see that this is the information given us the height. Okay, this is the center of the base to the ground, which is 10 feet. And then the radius of the base, which is 5 feet. It's given to us, okay, guys. And also, you see when the water goes up, up, up. At the moment when the water is 6 feet here, high, and then it asks us, okay, what is the water, the rising rate? Okay, so how do I think about that? Well, as you can see, guys, first of all, this is the volume of a conical, and this x stands for the radius of the base, okay, and then this stands for the height of the conical, and which is 1/3 pi x squared times y, okay, times y. And as you can see, V stands for the volume of water at time t. Okay, X stands for the radius of the water surface at time t, and Y stands for the height of the water at time t. And one thing we can tell, guys, do you realize that actually you see this is X. I just use a different color. This is Y, right? This is Y. And do you see that actually X and Y is always proportional, right? You give an X and then the corresponding Y is proportional. As you can tell that this is what we can write. So it's X over Y actually equals 5/10, because this, right, triangular, it is similar to this, right, triangular, and then so the ratio of those two sides is equals the ratio of this over this, and we already know that this equals 5/10. So what do we get? Well, we can get a relationship between x and y, which gives us is y equals 12x. Okay, it's pretty, right? This equals 1/2, so we can get y equals 2x. What our focus on is actually, you can see that we try to figure out, okay, when y equals 6 feet, what is dy dt, right? The level rising, right? When the height is 6 feet. So, but this equation involved with not only the radius of the water surface, but also the height of that place here. We are focusing on, or we are interested on, about the dy dt. So one thing I can do is to reduce the right-hand side of the equation from 2 variables into 1 variable. Since we are interested in the height, so what we can do is we can set x equals y/2, right? And then make one substitution. Okay, make one substitution. So v gonna be 1/3 times pi times y squared over 4 times y. That gonna give us is, well, so it's pi y cubed over 12. Okay, 12. So, okay. And then we can use the implicit differentiation on both sides because V, the volume of the water level, is a function about T. Y is the height of that water, of that conical shape here, is also a time, a function of time t. So if we take the derivative on both sides, we have dv dt equals pi over 12 times 3y squared times dy dt, okay, times dy dt. And from here, you see, guys, we pretty much get everything. We have our dv dt is given, it's 9, you know, I ignore the unit. And then y here equals 6. So what you can do is you can plug into here. Let me drag it here. You're going to have this 9 equals pi over 12 times 3 times 6 squared, and then times dy dt, and then you can actually solve what is your dy dt. Okay, so that's actually gonna give you, let's see, yeah, so interestingly, this gonna give you is 1 over pi. Okay, and then that's gonna be the rate of the height, the rate of change for the height, okay? And that is exactly the part, you know, that is how fast is water level rising when the water is 6 feet deep, which is exactly asking us what is rate of change of y when y equals 6, okay? Of course, for here, guys, I ignore the unit, we should be feet per second per minute, okay? So this is the example about the related rates. Again, guys, there are tons of problems in the related rates. Again, there is no like a uniform method. Each problem is different. Meanwhile, it's the same. It's different is you know, the problem background might be different. It could be one car chasing another car, right? It could be you pump the air into a fixed shape, and then the length of one part is changing, and then the volume is changing, or something like that, or right. So or you have something, you know, you have infinite many numbers in the related rates problem. So they're different. They're the same. Why? Because all of them, it follows the same procedure to solve for them. You read the problem, right, and then you trying to visualize the problems and list the useful information, and then based on the condition, and then you trying to construct one equation that have the related quantity. We take the derivative of both sides, and then they form the related rates, and then correspondingly you can solve the problem. Okay, so work hard, and then work more problems, and practice makes perfect. Okay, so I'll stop here for this section, and then this is the last section in chapter 3, and then we'll move on chapter 4. Okay, so I'll stop here, and I hope you enjoy this video.